In this video, let's talk about power consumption in digital circuits. So static CMOS, as you all know, has a symmetric voltage transfer characteristic. It has a full voltage swing at the output and it has high noise margins. And hence, because of this superior robustness, it allows for design automation and it's generally the technology of choice in today's integrated circuit design. So let's now look at the power dissipation in these circuits and let's look at ways in which we can design to optimize for this power dissipation. We'll also try and develop a figure of merit when we have to consider optimization for power consumption. We'll look at some of the key contributors to the power consumption and look at a few design techniques that might help to mitigate some of the high power issues. So let's first think about the basic CMOS inverter, and I'll use this inverter as a representative of a digital circuit. So when the input or when the inverter is in static condition, that is when the input is not changing, logic 0, then the output is at logic 1. In that case, there is very minimal to zero current flowing through the transistor chain. When the input is a logic 0, the NMOS is turned off, the PMOS is turned on. So this NMOS restricts the current that flows from the power supply to ground. Now in our models that we've used so far, we assume that the current is 0, so it's perfect circuit in the sense that no current flows from supply to ground. But in reality, we know that there is a leakage current that is associated with the transistor. So a certain leakage current will flow through this circuit when the input is at a 0 or a 1. But for now, we'll assume that these currents are so minimal that we won't consider them in the power consumption. So I'd say that the power consumed in steady state is essentially 0 when we consider ideal MOS characteristics. So the power is consumed only when you're charging or discharging this load capacitance. That is during the dynamic operation of this gate. That is the only time when there is power consumption in the circuit. Let's look at the case when the output is rising from 0 to VDD. Now, as the output rises from 0 to VDD, a certain amount of energy is drawn from the power supply. And how do we find that out? We find that out by figuring out what is the product of the current that is drawn from the supply and the product of the supply voltage integrated over the entire duration of the rise of the charge in the capacitor. And so if you work out the math, it works out to CL VDD squared. That is, the energy that is consumed from the power supply is given by the capacitance times the square of the supply voltage. Now, what is the energy stored in the capacitor? The energy stored in the capacitor is given by the integral of I times V across the capacitor, which in our case is V out. And if you work that integral out, it works out to half CL VDD squared. So while CL times VDD squared is consumed from the supply, only half of it is stored in the capacitor. So the rest of the energy is essentially dissipated during the charge up process. So it is dissipated through this PMOS transistor. And now when you discharge this capacitor in the next cycle, then this half CV squared that was stored in the capacitor at the load is going to be discharged through the NMOS transistor. So in effect, what you see is that the energy that is stored in the CMOS inverter does not have a dependence on the size to first order. It depends only on the intrinsic capacitance of the inverter. And for an entire switching cycle, so suppose I take the input from low to high to low, you have a fixed amount of energy that is going to be taken from the power supply, and that for one single transition is given by CV squared. And so if this transition happens F number of times in a second, then the total power that is going to be consumed from the supply is going to be given by CL times VDD squared F. So you see here is that the dynamic power of this inverter is directly proportional to the total load capacitance that we have connected to the circuit. It's proportional to the square of the supply voltage and it's proportional to the frequency of the circuit. So if you want to operate the circuit at a faster rate, you essentially need to burn more power. If you want to drive long lines where the capacitance is going to be larger, you're going to burn more power. And you'll see that VDD is a strong indicator of the power that is going to be consumed in the circuit. So for example, if you look at certain nodes which are not the clock nodes, for example, it's not necessary that all nodes switch at all times during a second, right? So many a times we denote the power in a gate, we normalize it by a term which is known as alpha, and alpha denotes the switching activity of the gate, right? So in the worst case, if the gate switches at every clock, then you're going to burn CL VDD squared F. But if it has a lower switching activity, then it's going to be tempered down by that switching factor. Another cause of power dissipation is essentially power dissipation that might happen if there is a direct path from VDD to ground in this circuit. Now, so far when we have done all the analysis in the inverter, we have assumed that the input voltages rise sharply. That is, there is no rise or fall time in the input signal. And therefore, what happens is the minute we start analyzing the circuit, one of these transistors switches off. So therefore, we never have a case where these two transistors are on simultaneously. But if you remember the VTC of the inverter, the VTC has current flowing through the inverter in case the input is not at 0 or not at VDD. So in case I have a fixed rise time or a fixed fall time at the input, then as the voltage transitions from 0 to VDD or transitions from VDD to 0, it is going to go through voltages at which both the transistors might be conducting current. So that is what I mean when I say that there is a direct path. The direct path kicks in whenever we have a rise time or a fall time for the input signal, which is normally always the case. And we model that typically as a triangular waveform. Again, this is an approximation. In reality, it is not triangular. But to keep the math simple, we'll model it as a triangular waveform whose peak is at I peak and has a duration of the TSC, where SC stands for short circuit. And this is going to happen during the rise time and the fall time at the input. So the total energy due to the direct path that can occur between VDD and ground is given by VDD times I peak TSC by 2 during the rise and the same power during the fall, leading to a net energy of VDD times I times the duration over which this current will flow. And so if I assume that I have a linear profile for the input slope, that is, if I assume that the voltage is changing linearly at the input, in that case I can write my TSC in terms of VDD and the VT of the transistors, and where TS is the total transition time, right? And so this gives you an idea of how much of the total transition time is actually in the short circuit mode. And you see here that it's a function of VDD and VT. So as you bring down VDD, and if your VT doesn't change much, then you see that this component gets lower and lower compared to what would it have been at higher VDD. Now the power dissipation in this direct path has two terms. So first is the I peak. Now if you look at the peak current that is going to flow through this inverter, that is going to be the saturation current across the two transistors. So the maximum current is going to flow when both these transistors are in saturation, and that is dependent on sizing. So if you have a larger transistor size, more current is going to flow through this path in when both the transistors are on. Similarly, you see that it's a very strong function of the ratio of the input and output slopes. And if you want to minimize this peak current, you basically want to minimize it by making the output time larger than the input transition time. So let's look at what I mean by that. So let's assume that our load capacitance is very large. So if our load capacitance is very large, this output node is going to transition slowly. So if my CL is very large, what happens is my input transitions much faster than my output transitions. And in the limiting case, I would have the case where the input has transitioned completely before my output begins to fall, right? Especially if CL becomes very large. And so if the input transitions completely, then essentially I don't have to worry about anything because the PMOS gets turned off. Suppose I'm looking at the discharge event of the capacitor, then the PMOS gets turned off immediately. So in this case, when my CL is very large or when my output is transitioning very slowly compared to the input, the issue doesn't exist. However, if I have a very small capacitance connected, in which case my output transitions very fast, then I'm going to have a region where my input is still transitioning, where my output has transitioned. So at that time, the current flowing through the inverter is going to be very large, leading to a higher power consumption. And so we normally model this short circuit current using a fake capacitance. Now, this capacitance is purely a modeling capacitance, and it is modeled as a capacitance TSC peak by VDD, and it is modeled parallel to CL. So it adds on to the load capacitance. So it adds on to the power consumption in the circuit. So if you think about the total power consumption is made up of three parts. One is the dynamic power consumption, which happens every time the input switches. Then you have the direct path consumption, and this happens because of the rise time or of the fall time of the input signal. And finally, you have the static power consumption, which, as I said, happens during the leakage of the current. So if you think about the three components, the first one is CL times VDD squared. The second one is VDD times I peak times TS, right? And this is the power consumption for a single transition from 0 to 1. And then you have the VDT times I leak, and this is the static power consumption. And typically in most digital logic, this dynamic power is the largest contributor to power in the circuit, because that is the one where we are getting work done from the circuit. So this is going to have the maximum contribution. This one unfortunately creeps up on us. So especially with scaling, you see that this component creeps up. And so we have to come up with different techniques to capture these and actually control the leakage in the static power. So let's talk about a figure of merit. So generally, in most circuits, you can trade off power for delay. Right? So you can construct a circuit which is going to be very slow so as to consume less power, but you'll see that that circuit is going to be not a very fast circuit. So generally, to make sure that we are taking care of both power and delay, people sometimes suggest using the power delay product or PDP as a metric. So it's a metric to assess the quality of design. And so PDP can be written as the average power times the delay or the propagation delay through the gate, and its units are in joules. Now let's assume that the gate is switching at the maximum allowable frequency, which is 1 by 2 times the propagation delay. This 2 times comes because the propagation delay is only from a single transition. If you look at a clock, it goes 0, 1, 0. So therefore the maximum frequency is 1 by 2. Again, if you ignore the contributions due to the direct path and the static, so if I assume that the average power is determined only by the switching frequency and the switching power, what you see is that the power delay product becomes independent of frequency, and it's only related to half CL VDD squared, or that is nothing but the average energy consumed per switching event of the circuit. And so the average energy consumed per switching cycle is just given as 2 times PDP. Now you see here immediately the problem of this PDP as a metric, because if I want to now make a very good circuit with respect to PDP, all I need to do is keep reducing VDD. But you know that you can't keep reducing VDD arbitrarily, because once VDD gets close to VT, then the drive currents in the transistor are going to get very, very small, and so the delay is going to be pretty long. In the sense, it's not going to be tenable to have such a circuit. Hypothetically, you can bring this PDP down to 0, but it doesn't capture the impact that it would have on the delay. And so therefore, what many people talk about, or what designers generally tend to use, is an EDP or an energy delay. So what we do is we take the PDP and we multiply it again by the propagation delay, and that gives you an energy delay product, which is given by P average times TP. In the previous case, if I assume that the power is purely only the dynamic power in the circuit, then I can write this as energy delay product is half CV squared times the propagation delay. Now, why is this useful? Let's look at, suppose I want to plot energy or delay as a function of VDD. Now, if you look at delay, as I keep increasing VDD, I'm generally going to get a smaller delay. And generally, delay tends to show a relationship equal to a 1 by V relationship. On the other hand, as you keep increasing VDD, because the energy is related to VDD squared, the energy rises rapidly as you keep increasing VDD. And so here's the trade-off that you're normally associated with. You're going to get low delays but at high energies, or you're going to get long delays at low energies. And so if I look at the energy delay product or the product of these two curves, it typically shows a minimum. And so that minimum would be the point that is minimized for both energy and delay. Now, obviously, this optimization equalizes the importance of energy and delay, and that may not be what you want to do in your module. So then you suitably weigh the optimization function to figure out where your optimal point would be for design. What I wanted to highlight here is that there is always going to be a trade-off between energy and delay. And so to find the optimum, you have to define what is the weight that you're going to associate with energy or delay. Now let's think of the modulators of power in most circuits. So the foremost modulator of power is the activity factor. Remember that the power in a circuit is mostly the dynamic power in the circuit. That is how the more the circuit switches, the more power it's going to consume. And so an easy way to manage power would be if you can either shut off switching of the circuit when you don't want to use it, or you figure out is there a way to reduce the switching probabilities in the circuit. So for example, if you think about clock gating, clock typically has the highest activity factor in a circuit because the clock is going to come 0101 continuously. But what you can do is for certain blocks where you do not want them to operate when you're not going to use their outputs, we normally use logic to gate the clocks. That way, those particular gates where the clock is coming in, those capacitances are not going to come into the clock, so you end up saving power. Now, what typically happens in such cases, you have to be careful because these logic paths which are in the clock, remember, clock is the fastest signal in the circuit. So these logic paths in the clock typically are the critical paths in the circuit. So a lot of care needs to be taken to optimize for the delay in these paths. So therefore, if you have a choice to design a path, in general, in path design, you would choose a path that has the lowest switching probability. So just a side note on the switching probability. Suppose I define Pi to be the probability that some node I in the circuit is at 1, then Pi bar is going to be the probability that that node is 0. And so the switching probability or alpha is nothing but the probability that the node was 0 in one cycle and becomes 1 in the next cycle. And so we talk about alpha typically as Pi bar P. So if I look at a random data node, then I'm going to see alpha is roughly 0.25. Again, for different gates, for different paths, you can come up with the switching factors for the various gates in a path. Now, the other modulator for power is known as glitches. And this happens especially when you have a path with a lot of branching. So if you think about the activity factor, the probabilities, activity factor, all of them are valid only when the gate delay is 0 or negligible. However, when you look at very long data paths, there sometimes, because of the fact that certain paths are longer than certain other paths, there exists a competition. So there can be nodes which essentially have a transitory output. That is, a node is supposed to be a 0, but because of the fact that a certain influencing input comes later, a node can sometimes switch transitorily to 1 and then come back to 0. And so this unintentional spike that you have in the node voltage can end up causing a much larger power dissipation. And so in some long chains, it actually raises the activity factor of certain nodes to greater than 1. So remember, clock has the highest activity factor of 1. But in case you have a circuit where you have glitches coming in, then those nodes are going to actually show activity factors of greater than 1. And some example circuits are ripple carries and multipliers. So in those circuits, you have to be very careful. So again, in general, when you look at design, when you optimize your design, you need to reduce the occurrence of glitches or figure out a way in which glitches do not impact your design. And so when you look at to design a glitch-free circuit, there are different techniques to be used, and you use them to ensure that the power dissipation is maintained and in control. Another modulator for power, which is direct, is the capacitance, right? So the load capacitance directly impacts the power consumed in the circuit. And so if you look at the capacitance, that can come from two parts. One are the wires and the other are the transistors. Now the wires, the only way to ensure that we're using the minimum required is to have good floor planning and placement techniques. So again, there are softwares available for this, and custom design involves a lot of optimizing of the floor planning to ensure that the capacitance is minimized. Now, as far as transistors go, choosing fewer logic stages and smaller transistors helps with power. But remember, these may not necessarily help with delay. So what we do is we use minimum sized gates in almost all non-critical paths. That way we ensure that the power dissipation in the non-critical path is less. And when I say non-critical, it means that the delay in this path is not limiting the delay of my module. And finally, what we can also do is use a slightly larger stage effort. So if you remember stage efforts, we tend to keep the stage effort at around 4. So if you can trade off delay for power, using a slightly larger delay for stage effort will not increase the delay much, but will help you a lot in saving the power because it reduces the sizes of the transistors. And so basically in other cases, especially if you're looking at fast circuits, we look at certain styles later on, you can also reduce the delay at the expense of energy. So again, energy and delay are something that can be traded off with each other depending on what the requirement of your module is. Now suppose I want to design a path and I want to size it up for minimum energy. How do I go up setting up the problem? So let's assume that we have a technology in which the smallest inverter has a capacitance of 3C. So any gate which has a logical effort of G and a parasitic delay of P with a drive of X, what the drive X means is basically making the gate larger, then it's going to have Gx times the gate capacitance, right? So the gate capacitance of this logic gate is going to be Gx into 3C, and the parasitic capacitance is going to be Px into 3C. Now the switching energy per gate depends on multiple things. We've looked at those. One is the activity factor, second is the diffusion capacitance at the gate, the wire cap at the gate, and the gate cap of the next stage. So if I work out total energy at all the nodes in the path, I'm going to basically sum up the energy at the individual nodes, and for each individual node I have the energy written as alpha times Ci, which is the net capacitance at the node, times VDD squared. But look at a fan out. So at every node I, suppose I have a certain fan out, then my total fan out at any node is given by sigma Gj into Xj, and this is the net capacitance that I have at every node because of the fan out. Suppose I also normalize the wire cap. So instead of using C wire, which is the raw capacitance, I'll normalize it to the capacitance of the inverter. So I'll call that a small Ci. Then essentially I can write my energy in normalized terms. So it becomes 3C VDD squared, sigma over all nodes, alpha I. This is the capacitance, this is the normalized capacitance of the wire. These are the normalized capacitances due to the parasitic caps, and these are all the capacitances that come up because of the fan out. And so if you look at the normalized energy, you have a normalized energy which can be written purely in terms of all the parameters of the path. And now you want to minimize this energy for some given delay. So this becomes your optimization function, and you minimize this so that the delay of the path is less than some maximum delay d. So this is how you would set up the optimization equation and then go ahead with the optimization. Now, as we have looked at the expressions for energy and power, voltage plays a very major role in power dissipation. And so changing VDD will affect the power quadratically. Now, one thing that helps as we made the transistors smaller is that once we push the transistors into the velocity saturated regime, the impact of the gate length on the drive current of the transistor reduces. And so therefore what you see is that by reducing the VDD, you don't have a huge reduction in the delay, right? Because of the fact that the drain field no longer impacts the current at the same way as it would have done in the long channel model. In velocity saturated transistors, you end up having not a lot to pay in terms of delay for reducing VDD. One way to work with this problem is what normally is done is the chip is divided into multiple voltage domains where each domain is optimized for certain circuits. So one example would be we use a high supply voltages for memories. So SRAM, because we want the cell to be stable, we'd use a high voltage for that. We'll use a medium supply voltage for processor because that would be an ideal mix for both delay and power. And we might use low voltages for the peripheral circuits which don't have to run at high speed. So I can have them run slower and therefore reduce the voltage of that particular module. And so we can also adjust voltages based on the operating mode, right? So the same logic. Now here these domains are fixed, right? This happens at the design level. So we fix the domains and then we push particular circuits into these domains. You can also do an voltage. So the voltage can also be adjusted based on the operating mode. So you can switch to a high voltage when the power supply is connected to the battery, for example. And when there is no power supply, when the laptop is operating in its battery mode, we reduce the power, we reduce the voltage, and therefore we are able to conserve more power in the product. Now, another point to note is if both VDD and frequency is reduced, then you see that the power reduces cubically. So therefore, by attacking both the supply voltage and the frequency, you can save a lot of power in your circuit. So let's talk a little bit about voltage domains. So what are the challenges associated with that? Primarily, you have to connect voltages for signals at different levels, right? And so you need to ensure that the signal that is crossing a domain is suitably changed as it crosses from low to high or high to low. Secondly, you have to also have some initial understanding to select as to which circuit goes into which domain. Again, this has to be done prior because you can't then randomly move circuits around. Third challenge comes about is routing power supplies to these multiple domains, because for a large voltage domain, you're going to have more current. So you need to ensure that the lines that are bringing in the power supply there are probably wider, or the bus is wider as compared to a domain which has a smaller voltage. So let's look at a specific case. Suppose I want to cross a domain from high to low. So I have two voltages, a VDD high and a VDD low. So if I have to cross a domain from high to low, generally it's not a problem because this node output is going to be higher than the required high for this node, right? So when this output node is a 1, its 1 is much stronger than the one here. And so therefore what's going to happen is this circuit is not going to have a problem responding to this one. What might be an issue is that because the voltage is so high here compared to the supply voltage, it is possible that this gate can switch faster than other gates in this domain. And so if you have a certain contamination delay, then this contamination delay here might be smaller. So you need to check and ensure that that doesn't affect your circuit. On the other hand, if you're going to cross from a low to a high, then it becomes a problem because a 1 here, the 1 at the output of the low domain may not necessarily be a 1, or it's a weak 1 for the high domain. And if you look at a worst case, especially when the voltage domain, when the VDDL minus the VDDH is less than the VTP of the PMOS, it is possible that this PMOS turns on when it shouldn't have, and then you're going to have a lot of power that might be consumed by this circuit. So therefore crossing from low to high cannot be done just as is. This crossing is generally avoided because this consumes power. So what is it that we do? So we use what is known as a level converter when we want to cross domains. And what that involves is essentially a slightly complicated circuit of this fashion. And so let's look at the case. When A is 0, N1 is turned off and N2 is turned on. Right? So this NMOS turns on. This NMOS pulls Y down to 0. Now when this Y is pulled down to 0, this P1 pulls X to 1. Right? And so therefore it ensures that this P2 is off at all times, which was what was the problem in the previous case. When A is 1, then essentially N1 turns on, N2 turns off, and likewise you'll see that P1 is off and P2 is on. So in this case both Y and X are 0, and this connection ensures that the PMOS is always on when, the PMOS is always off when the NMOS is on, right? So therefore it ensures that at no time are you going to have a direct path from supply to ground, and hence you can arrest the power dissipation that normally happens in such a crossing. Now the drawback of this circuit obviously is it comes at an added cost of delay and area and you'd require more power at the crossing. So again, you don't want to do a lot of crossings, but crossings can be managed using circuits which are known as level converters. Another way to manage power is known as clustered voltage scaling. That is, we use two supply voltages in the same block. And again, as we looked at before, crossing from high to low is generally not a problem. It is the low to high crossing which is an issue. So what we do is early gates in the path use the high voltage, and then non-critical paths we use the low voltage. Now we assign the voltages such that a path never crosses from low to high within a block. And if there is a need, we keep it very selective, the crossing from low to high, normally in registers, and there we use level converters. So again, point is use the converters, but use it in a minimum fashion, so overall you end up getting a gain in the power dissipation. Now the drawbacks, obviously you need to worry about two supply rails, which means that the design might be slightly wider in area. And second thing is, because of the fact that you have two cells, one which has a slightly higher power supply, you will need to deal with the end well spacing, for example. So well spacing changes because one has to isolate transistors at a much larger VDD, and hence that would mean that you're going to have a larger spacing between low to high gates. So these small things come in, but if you use a lot of these where you're stacking these L and H gates next to each other, you're going to end up bloating the area of your module. So again, reducing the number of transitions from low to high would help. Another way of managing power is known as dynamic voltage setting. So in the previous case we looked at where a priori we are assigning voltage domains and we are letting the circuits run at those specific voltages. Now this is known as dynamic, where we are changing the supply to the circuit based on what the circuit needs. So it's sometimes also known as dynamic voltage or frequency scaling. So what the two ways we do it is, we reduce the clock frequency to the minimum sufficient to complete the task on schedule. So this requires you to have some sort of a lookup table or some sort of knowledge to know what should the right frequency be for a given load. And once you do that, then we reduce the VDD to the minimum required to sustain that frequency. Right? So because we optimize both VDD and frequency, you end up getting a lot of saving on the power. So for example, we have, suppose some core logic here. We have a DVS controller, and the core logic has certain circuits which are able to supply information regarding the workload and the temperature. And this temperature is a proxy for the power dissipation in the circuit. So this workload and temperature are supplied to this DVS controller, which then supplies signals which can control the frequency in the core logic, normally through a PLL which might be located in the core logic. The voltage control is achieved using a switching voltage regulator, and again you use a larger voltage as Vn, and that voltage is suitably modulated based on this signal, and that particular VDD is then sent to the core logic. So you see, obviously this design will require a lot more modules that need to be designed, so the area of this is going to go up, but it's going to give you a much better control on the power dissipation in the logic. Now, what does a switching voltage regulator do? It steps down the high VA into VDD. The core logic, as I mentioned, consists of a PLL or a clock synthesizer to generate the clock. This DVS controller chooses the voltage with a pre-characterized table. So again, this needs some work to be done a priori, in which you're able to tell your design what is the frequency I need to select for a certain workload and a certain temperature. And so in this case, now if I plot normalized energy versus percentage maximum performance. So what I'm trying to tell you is, what we're trying to do here is we're trying to reduce the power. So we are trading off performance, and hence we're going to get a lower energy. So if I just used a fixed supply voltage and basically finish my workload and shut down power to the module, then essentially my delay or my energy versus performance, and performance can be thought of as delay, my energy delay typically shows this trade-off. That is, my performance becomes worse and worse, my energy also improves. Now, if I have a continuously adjustable voltage supply, this would be the dream, where the voltage changes for every small change, like an analog circuit. Then you get a very good energy performance delay, where you get good savings for the match performance. So if I look at a line parallel to the y-axis here, for the same performance, I'm going to get a much better energy consumption for my module. Now this is difficult to implement, takes a lot of area and a lot of additional control circuitry here. Sometimes we implement it as 3 levels of performance. So in that we break this straight line into 3 different lines, and so we would probably pick 3 different VDD levels. That makes this design much simpler, and that gives you respectable saving in terms of the energy. And DVS normally is extended from VDD to around 50% of VDD. Now another way to do power gating is basically, if you have a block, you switch the power to the block when you're not using the block. And so that way what happens is it arrests both the dynamic power and it arrests the static power that might be burning in this block. So this block basically consists of a header, and this header switch, the duty of this header switch is essentially to control the power supply that eventually flows into the gated block. So you use a sleep signal to activate or deactivate this block. We also use the same signal at the outputs just to ensure that the outputs don't take forbidden values as this switch switches. Right? So for example, when the switch sleeps or when it transitions from sleep to no sleep and vice versa, these voltages can flicker around, and you don't want that noise to be sent on. So we normally gate these output voltages using the sleep bar signal. So what are the design challenges? First thing is, these header switches that we are adding on to these, they are going to add on capacitances in the path. So we want to ensure that this header switch adds a minimal delay during the active operation. In other words, also we want to ensure that this doesn't add a lot more leakage to your circuit. So we want to ensure that these transistors have low leakage also. And also what you'd see is when you have a circuit like this, right? You remember all these nodes have capacitance. So transitioning from active to sleep and vice versa is going to take some time. And power gating becomes effective only when the block can be turned long enough. So again, it's probably not prudent to keep switching on and off the block every time. As long as you have a use case where the block can be switched off for a certain amount of time, which is long enough, then these techniques help you with managing power. Another interesting way of managing power, and this is very common in today's technologies, is having what is known as a multiple threshold type tree. So if you think about transistors, if I plot I off versus I on, you typically have different transistors. So the foundry would give you different transistors flavors. Basically, you have what is known as a high VT transistor, a standard VT transistor, and a low VT transistor. So the high VT transistor is going to have the lowest off current, but it's going to have a low on current also. And likewise, the LVT transistor is going to have the highest on current, but also at a larger off current. And so basically what you create, and the advantage with these 3 transistors is generally tend to have very similar standard cells. And so this helps with when you're placing it in a place and route, it generally helps that these cells can be placed close together. And so normally what we would do in such a case is we'd use high VT devices everywhere unless we are in the critical path where we'll use the low VT devices. Now the key point again to keep in mind here is these additional VT devices require additional mass. So adding more flavors here or adding different kinds of VT devices here is going to increase the cost to fabrication of the chip. Sometimes for IO devices where we have to run IO devices at much larger voltages than the voltage in the processor, we also have thick gate oxide transistors, and those are able to sustain the higher voltages normally that are required at the IO. And so those are also kind of flavors of transistors that are available. So normally you have a suite of transistors from which you can choose. Now these high IO transistors with larger voltages obviously are going to have a different layout compared to this. But within the same voltage domain, you should be able to switch easily between these 3 different kinds of transistors. Now, because of the fact that power management has become so critical, over the last few years there has been a trend towards parallelism. That is, move to a large number of simple cores rather than have one large core which has a lot of capacitance. And this also helps you handle data, tasks, and parallelism. So what happens here is that the focus has shifted from purely a clock driven high power circuit to something which can run multiple things in parallel. And what happens is this helps with having shorter wires, and hence you have faster memory access. Again, lot more memory has now showing up in the architecture, and that's because memories have much lower power densities and also low activity factors. And then there's a rise in basically splitting things away from the processor and creating these accelerators which can offload the tasks which are normally handled with the processor. And finally, there's also more towards heterogeneous architectures where essentially we put all these together and you have different techniques of stacking these chips or modules together so that you're able to achieve a design which has low power consumption. So to conclude, we've looked at key contributors to power dissipation. Various methods are available to mitigate the impact of power or control the power dissipation by trading off performance or area. What technique you use will vary on the product and depend on setting up the right optimization function and also finding out what is the right figure of merit you'd use to evaluate your design.